Sections 4.1 and 4.2. Section 4.1 is scatter diagrams and correlation. The response variable is the variable whose value can be explained by the value of the explanatory or the predictor value. A blank is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram, and that's what this is. This is a scatter diagram. Okay? Scatter diagram. All right. The explanatory variable is plotted on the horizontal, and the response variable is plotted on the vertical axis. So table 1 has club head speed in miles per hour and the distance in yards. This is a golf club swinging and a golf ball flying in the air. So 100 miles an hour, the first one, it went 257 yards. 102 miles an hour on the second club head speed, 264 yards. 103 miles an hour, 274 yards. 101 miles an hour, 266 yards, and so on and so forth. All right, so caution, do not connect the points when drawing a scatter diagram. So figure 1, the scatter diagram shown here, all right, for table 1 is club head speed increases, the distance the ball travels increases. You can see this relationship, right? As this gets bigger, right? So there's a relationship. Even though those points are not in a perfectly straight line, I drew a line kind of that represented the general tendency of them there, right? As one got bigger, the other got bigger. And the club head speed is the explanatory variable. The distance the ball travels is the response variable. So the faster the club head speed, the further the ball goes. All right. So here, scatter diagrams show the type of relation that exists between two variables. Our goal in determining scatter diagrams is to distinguish scatter diagrams that imply a linear relation, a non-linear relation, or no relation. So figure 2, which you see across here, displays various scatter diagrams and the types of relations implied through them. So this one here, it's explanatory and response and explanatory. Right, the explanatory is down here, response on the vertical, and this is a linear. It's pretty much a straight line. It's pretty much a straight line. So now let's look at the next one. This is also a linear. All right, but here, as one gets bigger, the other's getting smaller. So it's a different kind of relationship as far as bigger, smaller goes, but it's still a line. It's still linear. All right, this one is explanatory. It follows a pattern, but it's not a line, so we call it nonlinear. All right, but it is still explanatory. I mean, it still has a relation. It's just not a linear relation. And then here, this one again kind of follows a curve. So it's not a straight line. It's nonlinear, but it does exist there. And then here, this thing is just sort of spread out all over the place. I mean, you could draw a line here, whatever. You know, you could do all kind of stuff, and it's no relation there. They're just kind of scattered all over the place. No relation. So two variables that are linearly related are positively associated when above average values of one are associated with above average values of the other. If one gets bigger, the other gets bigger, okay? So, and below average values of one variable are associated with below average values of the other variable. So as one gets smaller, the other gets smaller. That is, two variables are positively associated if whenever the value of one increases, the value of the other increases. Two variables that are linearly related are negatively associated when above average values of one are associated with below average values of the other. So another way to say this, when one variable increases, the other decreases. All right? That's what's happening here. This is negative. This is positive. All right? It's just like the slope of a line, by the way. This line's going uphill from left to right, positive slope, downhill, negative slope. So that's what's going on there. And then in other words over here on the side, if two variables are positively associated, then as one goes up, the other goes up or tends to go up. And if they're negatively associated, then as one goes down, the other tends to go down. Now, remember, it's an association, so it doesn't necessarily mean that every time something goes up, the other one goes up. It tends to go up. So in general, if you kind of follow that line would generally increase or decrease, whether it be positive or negative in that situation. So just because something is bigger doesn't mean the other value is automatically bigger, but it would tend to be bigger, right, for the response variable. The linear correlation coefficient, or it's also known as the Pearson product moment correlation coefficient. Say that real fast 8 times, right? Is a measure of the strength and direction of the linear relation between two quantitative variables. The Greek letter rho, that's like a little lowercase p. Rho represents the population correlation coefficient, and R, the sample correlation coefficient. And again, Greek letter rho for population and regular English letter for R for sample. Sample linear correlation coefficient, R equals, that sigma means a sum. Look, it's xi minus x bar over s sub x. All right? And then this one is yi minus y bar over s sub y. So you know what this is? This is a standard score for each x and a standard score or z-score for each y. So you're taking the standard scores and multiplying the x standard and the z standard together, summing all those up, and then dividing by n minus 1. Remember, that's our degrees of freedom. N is the number of individuals in our sample. We talked about how we can pick anything we want for the first n minus 1, but then the last one is sort of boxed in so that the numbers work out to be the mean or the standard deviation or whatever it is we're looking for. So we need it to be that. So it's the one less. An equivalent computational formula is shown here. I mean, look at this. The sum of xi, yi minus the sum of x times the sum of y over n, all over the square root of the sum of xi squared minus the sum of xi in parentheses squared over n, and then the equivalent square root with y's in it. Yeah, that's right. So the good thing is, your TI-30 XIIS or the XIIS multi-view or your TI-82, 83, 81, 84, whatever you have, TI-80 something, they all do this for you. You can enter your data in. You can get the linear regression line, and it will give you your R. I'm actually not even sure if you have to get the line. You can find the correlation without doing the linear regression line, but it'll give you the correlation coefficient. The closer you get to 1, the stronger positive. The closer you get to 0, the stronger negative. And that's under this properties of the linear correlation coefficient. It'll be between -1 and 1 inclusive. If R is plus or minus 1, it's a perfect linear relationship. So if it's a positive 1, it's a perfect positive relationship. If it's -1, it's a perfect negative. That means if you were to draw a line, it would go through every single point. It's perfect. No point lies off the line. The closer you get to +1, the stronger the positive association. The closer you get to -1, the stronger the evidence is for a negative association. That's number 5. Number 6, if R is close to 0, then little or no evidence exists of a linear relation. So R close to 0 does not imply no relation, just no linear relation. That's important. Number 7, the linear correlation coefficient is a unitless measure of association. So the unit of measure for x and y plays no role in the interpretation of R. Doesn't matter what x and y are, what their units are, correlation coefficient has no units. It's not affected. But it doesn't matter if it's miles, feet, yards, dollars, pennies, number of desks, number of students. It doesn't matter. It's not affected by it. Number 8, the correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern could affect the value of it. So if you have outliers, if you have things that maybe are something way off by itself, an outlier, or something close to an outlier, then it can affect the correlation coefficient. It is not resistant. So here's a caution. A linear correlation coefficient close to 0 does not imply there's no relation, just no linear relation. That was in number 6. We want to caution and say that again here. For example, the scatter diagram in figure 4H indicates that two variables are related, but the linear correlation is going to be 0. So let's look at 4H. Here's 4 and here's H, right? There is a definite correlation there, right? But it's a curve. It's not a line. So the R is going to be 0 there, but that doesn't mean there's no relation. There's just no linear relation. Linear meaning line, right? So let's look through these. Look at A up here. This is A. This is a perfect 1. Perfect positive, right? Straight line goes through every single one of those points. This one, strong positive, right? All those points are really close to that line. Here, this is also increasing. It's positive, but it's not as strong as this one, right? So this is what we call moderate positive. And then this one, again, perfect all on the line. That's a negative one, exactly a perfect negative. This is a strong negative. And then this one, again, is still negative, but it's not as strong as this one, so we call it moderate. It's a moderately negative linear relation there. This one, no relation at all. This is no linear, this is no linear and also has no relation, really. I mean, there's nothing that really follows. This one is no linear relation, but it has that shape that we talked about already. It definitely follows a shape, just not a line. Just not a line. So the testing a linear relation, determine the absolute value of the correlation coefficient, find the critical value. If an absolute value of the correlation is greater than the critical value, okay, so here, in other words, we use two vertical bars, as in 5 or -4. Recall 5 is 5, -4, right? You know these things. So you have this critical value, and it's depending on your n, right? Your n, your sample size. So, for example, if we had 7 things in our 7 elements in our sample, what is our critical value? Right here, it's 0.754. It's 0.754. So if n equals 7, then this is going to be 0.754, and this is going to be -0.754. Those are going to be my critical values. So what if I find R? What if I find R for this sample of 7, and what if I get R to be 0.813? Well, here's 0.813, right? And guess what? That falls within this range of what? Positive association. So that would be positively associated. So then what if I find R to be 0.691? So here's 0.691. That falls inside here. That is no linear relation, right? So that's what this table means. That's how you interpret this. That's how you do that. So you find R, and if you know your sample size, then you go in there and say, okay, what are my limits on this thing? And if you'll notice, the bigger your sample size get, the less your correlation has to be there to show a relationship. And that just, right, the more data points you get, it's going to be harder to get a perfect linear relation. So the R coefficient can go down but still be positive or negatively associated. Okay, so it's got to be between that value, that critical value in 1 or that critical value in -1 to show association. If it's in between the two critical values, there's no linear relation there. So is there another way two variables can be correlated without there being a causal relationship? Yes, and it's through something called a lurking variable. And it's exactly what it sounds like. I was reading in my Star Wars book, actually. One of the 3 or 4 books ago, and this character was lurking in the shadows. They were watching some people in a cantina, and they were waiting for them to leave, and they were lurking in the shadows. So it's exactly what this sounds like. It's a variable that's kind of lurking. It's in there. It's in the background. It's in the shadows, and it's affecting the outcome, but it's not maybe the one that we're interested in. It's not the one that we thought had something to do with it. So there's some sort of relationship going on, but it's not necessarily causal. So a lurking variable, so this is going to be the same 2 words here. A lurking variable is related to both the explanatory and the response variable. So you can have lurking variables that are related and there's something going on there, but they're not necessarily causal, right? The least squares regression. The least squares regression line is the line that minimizes the sum of the squared errors, or what we call residuals. All right, and that's sort of like when we had standard deviation, how far something is from the mean. This is a little more complicated because it's a line, but if you take a line and you figure out the distance back to that line, it's basically minimizing the total distance of all the points from the line. So when we go back, let's just look back for a second. When we go back to these here, if I did, that would not be the least squares regression line, because look, all these distances over here, right? too far away. But maybe something right through here where if you take all the distances of these points, right, and that would all it would be as small as you could get them right through there, okay? So this one, might be right through here. This one, might be like that, or actually maybe more like that, okay? So, but that's your least squares regression line. This line minimizes the sum of the squared vertical distance between the observed value y and the predicted value y with that little, when you see y with this character, that's y hat. You read that y hat. Okay, and you can have x hat, m hat, q hat, whatever. You can have it. It doesn't have to be x and y. We typically talk about those things, but y hat here. And we represent this as minimize the sum. This is the sum. That's the sum. Minimize the sum of the residuals squared. The residuals squared there. So the equation y hat minus b1, that's b sub 1x, plus b sub 0, where b sub 1 is, look, there's r, the correlation coefficient, and it's the s sub y, which is the standard deviation of the y's, over the standard deviation of the x's. That's the slope of the least squares regression line. And then b0 is the y bar minus b1 times x bar, and it's the y-intercept. Now, lucky for you, those calculators I mentioned earlier do this too. You do the linear regression line stuff, and it gives you b1 and b naught, b sub 0. We call it b naught, NAUGHT. All right. So you can find r, b naught, b sub 0, b sub 1, r. You can find s sub y, s sub x, all those things, and y hat. That equation. If you have some of the graphing calculators, you can actually find the least squared regression line, and then you can just go into y1 equals or y2 equals, and you can actually enter the least squared regression line, and it'll put it in there for you. You don't have to type it or memorize it or anything. It'll put it straight in there for you and then graph it. So I have posted in Canvas a review, sort of 10-question review of Chapter 4, Sections 1 and 2. So I want you to take that. I have the answers posted, and actually the answers are in the notes. So these notes here that you printed, if you keep going, if you turn the page, there'll be 3 or 4 or 5 more pages of 10 questions. And I want you to work on those 10 questions, and then the answers are also posted there. So work on those and look at that Section 4.1 and 4.2 review. That's sort of like a test review, multiple choice kind of thing. It has a few free response on there too. All right, so I hope this helps with Chapter 4.